Welcome back, everyone. We're now going to talk about the two other steps of urine formation, and they are tubular reabsorption, so be able to describe how tubular reabsorption occurs and how it takes place. And the third step then, describe tubular secretion and state the solutes that are secreted. Now remember that up to 180 litres per day pass through the nephrons of the kidney. Most of that fluid and its contents has to be reabsorbed back into the blood. And so tubular reabsorption then is the return of 99% of all of that filtered water and many solutes to the blood. And this little schematic, just, to reinforce this. Once glomerular filtration has occurred, all of that water and solutes enters the glomerular capsule. And then in there, starting in the proximal convoluted tubule, most of these solutes and water is actually returned back into those peritubular capillaries, which will then, join with the venous circulation. So tubular reabsorption occurs as filtrate flows through the lumens of the proximal convoluted tubule or the proximal tubule or the PCT, the loop of Henle, the distal convoluted tubule or the DCT, and the collecting ducts. And this actual, tubular reabsorption for different solutes goes via different sort of transport mechanisms. So it results because of passive diffusion down concentration gradients, also facilitated diffusion. Again, this is passive. It's still using a concentration gradient, but transporters to transport different solutes. Active transport requiring energy in the form of ATP to push solutes against a concentration gradient, from an area where they're low in concentration to an area where they're high in concentration. We also have symport, and symport describes, the transport of two solutes in the same direction. Remember, antiport or countercurrent transport describes the transport of two solutes in opposite directions. And then, of course, we have osmosis there for the movement of water. And so tubular reabsorption is crucial and it plays many useful roles. Firstly, reabsorption of water from the filtrate back into the blood will decrease the amount of urine produced. And so will also help to maintain body fluid volumes. Tubular reabsorption will regulate fluid and electrolyte balance and blood pH. And of course, the regulation of acid-base balance of the blood and the electrolytes in the blood is vital for overall body functioning and homeostasis. And so tubular reabsorption involves the reabsorption of water, sodium, glucose, and bicarbonate ions and other things as well. Now, tubular reabsorption occurs in the proximal convoluted tubule. And you can see here that this is a really sort of active site for reabsorption of lots of different things. So glucose, sodium, amino acids, potassium, protein, calcium, all of those other things that you can read there yourself. So most reabsorption occurs in the proximal convoluted tubule. However, it also occurs in the loop of Henle. In particular, this descending part of the loop of Henle is permeable to water. So that's just a structural feature of the loop of Henle where water can be reabsorbed back into the peritubular capillaries. Now, the distal convoluted tubule and the collecting ducts are under hormonal control. Okay, and those hormones for water being antidiuretic hormone and for sodium being aldosterone. So just getting an overall picture of this, various portions of the nephron differ in the capacity to reabsorb water and solutes. Much of the reabsorption and secretion, which we'll talk about in a minute, occurs passively via concentration gradients, but the amount of water that is reabsorbed or lost is tightly regulated. And remember, again, I'll keep stressing it, it's under hormonal control. This control is exerted directly via antidiuretic hormone and aldosterone, and indirectly via renin, because renin is going to lead to angiotensin II and therefore aldosterone. Most water, though, is recovered in the proximal convoluted tubule and the descending part of the loop of Henle and in the distal convoluted tubule, and only about 10% of it reaches the collecting ducts. The collecting ducts then, influenced via antidiuretic hormone, can recover nearly all of that water passing through if we are dehydrated. So if the body needs to reclaim that water, antidiuretic hormone will be secreted from the posterior pituitary, and nearly all of that water passing through will move via osmosis from the collecting ducts into the interstitial fluid and then into those peritubular capillaries or vasorecta. And then, they can also, if you're very well hydrated, your posterior pituitary gland doesn't release antidiuretic hormone, and so that water then passes through. We'll talk about that in a bit more detail later on. So just getting this again, most of the reabsorption occurring in the proximal convoluted tubule. Some water then getting reabsorbed in the descending part of the loop of Henle. We have the ascending part of the loop of Henle, which is permeable to solutes but impermeable to water. So solutes can move out and into the peritubular capillaries. The distal convoluted tubule can recover some sodium, chloride, bicarbonate, and water. And then we also have, of course, the collecting duct there for water as well, and some urea. So when we look at this here, you can see that nearly everything that's really vital for the body that gets filtered, nearly all of it gets reabsorbed, except for creatinine down the bottom, because that's a waste product, right? So water, nearly all of it is reabsorbed back into the blood, and 1 to 2 liters then excreted per day on average. Proteins shouldn't be found in the urine, so you can see that nearly all of the protein that's filtered gets reabsorbed. Same for sodium, and of course same for chloride. Bicarbonate's the same. Glucose, now if you have normal glycemic control and therefore normal levels of blood glucose levels, when we eat, our blood glucose levels spike, and then under the influence of insulin, that glucose is removed into the liver or into skeletal muscle cells or into adipocytes. So under normal conditions, all of the glucose that's filtered into the proximal convoluted tubule should get reabsorbed, and you shouldn't have any glucose in your urine. However, in somebody who has diabetes and this amount that's filtered is much, much higher, there is just not enough little glucose transporters to remove that glucose back, across the cells of the proximal convoluted tubule and back into the blood, so that glucose stays in the urine. And we've talked about this before, and that causes glycosuria, and it's a sign of uncontrolled diabetes. Urea, then some of it is reabsorbed, some is excreted in urine. And creatinine, as I mentioned, about 1.6 grams of that is filtered. None of it should be reabsorbed into the blood because it's a waste product, so it should all be found in the urine. Right, so let's have a look at reabsorption in the proximal convoluted tubule. And remember in the PCT that this is the major site for reabsorption. So there's lots of things going on. And it's responsible for the majority of reabsorption. And by the end of the proximal convoluted tubule, the filtrate volume is reduced by 65%. Okay, what I want to show you here is we do have different membranes. We have basal membrane and an apical membrane. So if I move to the next slide, this is what we're looking at. We're looking at these cells that line the proximal convoluted tubule. They have this apical membrane that is facing the lumen of the proximal convoluted tubule. So this is the membrane that's in contact with the filtrate. And then we have this basal membrane here that is facing the interstitial space. Now, this is really intriguing. What drives reabsorption is this pump here. So we have a sodium potassium ATPase. It requires ATP, right? And it's moving sodium into the interstitial space from these cells lining the proximal convoluted tubule, at the same time putting 2 potassiums back in. Now, if you remove 3 sodiums from inside the cell, you're going to create a concentration gradient where the concentration of sodium here is greater than it is in here. And that's going to allow sodium then to move down its concentration gradient into the cells lining the proximal convoluted tubule, and then they're going to be pumped out, right? Now, this is so cool because you can see with this that this movement of sodium from the filtrate into the cells is coupled with the transport of lots of other things, right? So you can see here, what's an important one for us to know about, that the movement of sodium here is coupled to the movement of glucose from the filtrate back into the proximal convoluted tubule cells. So that's a symporter, right? You can see an antiporter here, where the movement of sodium from the lumen of the proximal convoluted tubule in results in hydrogen being pumped the other way out. So that's really cool. Now we have these exchangers or countercurrent transporters. So if I go back here now, and you don't need to memorize all of this table, right? But I just want you to sort of get the overall view that, you know, it has a great length, the proximal convoluted tubule. The cells have those microscopic extensions, being those microvilli, that increase that surface area to allow for reabsorption of lots of solutes, and lots of mitochondria there to drive that active transport. So the proximal convoluted tubule reabsorbs a greater variety of chemicals than any other parts of the nephron. So you can see across, you know, the basal membrane, all of these things here getting transported into the interstitial space to be returned to the blood. And then, of course, we also have across the apical membrane, so movement from the filtrate in the lumen across the apical membrane into those cells. So the things to remember here, everyone, will be sodium, would be, you know, potassium and chloride, amino acids and glucose. They're all really important things to remember. And remember as well that if you're going to be moving solutes such as sodium and chloride from the filtrate into the tubule cells and then into the peritubular cells, that is going to cause then a concentration gradient for water to move from the filtrate into the proximal convoluted tubule cells, into the interstitial space, and then into the peritubular capillaries as well. And that's what you're looking at down here. The bottom of this figure is showing you the movement of water via osmosis. And that's, you know, because of the movement of all of those solutes changing that osmotic gradient and pulling that water with them. So with tubular reabsorption, sodium is actively transported out of the tubule fluid and into the blood. And that's what then causes that, you know, concentration gradient for sodium then to move from the lumen of the proximal convoluted tubule and to transport lots of other things with it. Glucose and amino acids are passively transported out of the tubule's fluid by sodium co-transport mechanisms. Chloride, phosphate, and bicarbonate ions move passively into the blood because of an imbalance in electrical charge. The urea, approximately 50%, moves passively out of the tubule. And as I mentioned, because of the movement of sodium and chloride into the blood causes an osmotic imbalance, that will then cause water to move via osmosis into the blood. And so if we look at this sort of overall sort of summary of tubular reabsorption and the role that it plays in urine production, in the PCT, sodium and most other substances that need to be retained are reabsorbed. Water follows passively, and as I've mentioned a couple of times, the filtrate volume is reduced by 65%. In the descending limb of the loop of Henle, water exits passively. There's very little movement of solutes, but by the end, you know, when you get right down to that U-bend of the loop of Henle, the filtrate volume is reduced by another 15%. In the ascending limb of the loop of Henle, it's impermeable to water, so water does not leave there, but sodium chloride and potassium are transported out of the filtrate and back into the peritubular blood. And then in the distal convoluted tubules and the collecting ducts, water movement out is regulated by antidiuretic hormone. If it's absent, water is not reabsorbed and dilute urine is produced. But if antidiuretic hormone is present, water moves out and concentrated urine is produced. All right, so that's all we're going to say about tubular reabsorption, and now moving on to tubular secretion. So tubular secretion then moves metabolic byproducts, drugs, molecules not normally produced by the body from the blood, so from here, back into the nephron. And I've just drawn, a couple of little shapes there to show you the movement of these molecules or ions from the blood back into the filtrate. Now, this can occur via active or passive transport. Ammonia, which is produced by epithelial cells of the nephron from the deamination of amino acids, simply diffuses into the lumen. So just going back here, when we're thinking about it with secretion, those molecules or ions or whatever have to, move from the blood into the interstitial space and then across the cells lining the renal tubules to become then part of the filtrate. Hydrogen ions, potassium ions, penicillin, maybe you've taken some penicillin as an antibiotic for a bacterial infection, it has to be cleared from the body. Furosemide, which is a loop diuretic that some people need to take, say, for heart failure, they're all actively secreted into the nephron via active transport or antiport. So remember that antiport being in exchange for another solute or molecule or ion, going the other way. Very briefly then, we're going to look at tubular secretion in the proximal convoluted tubule and the loop of Henle. Okay, so secretion is really important in waste removal. And you can see here in the proximal convoluted tubule, we have secretion of lots of different things. They're moving into the nephron tubule here. So things like urea, creatinine, uric acid, bile salts, ammonia, the catecholamines, so noradrenaline and adrenaline, and many different drugs as well. And this is how they're permanently removed from the body. Acid-base balance is, I should have pointed out as well, some urea there getting secreted in the loop of Henle. Acid-base balance is really important. The pH of the blood must be tightly regulated. So when pH decreases, so as the blood pH starts to get more acidic, there's going to be increased secretion of hydrogen ions and also increased reabsorption of bicarbonate anions to buffer the pH of the blood. And overall, then that will lead to an increase in the pH of the blood plasma. When blood pH increases, so it becomes more basic or alkaline, then the opposite happens. There's going to be less secretion of hydrogen ions into the filtrate and less reabsorption of the bicarbonate anion from the filtrate back into the blood, and that will then cause a decrease in the pH of the body fluid back to homeostatic ranges. And then tubular secretion also occurs in the distal convoluted tubule and collecting duct. So we're over here, everybody. We get secretion of hydrogen and potassium ions and also ammonium ions. And secretion again of those hydrogen ions increases with an increased blood hydrogen ion concentration. So obviously as the pH is decreasing and becoming more acidic. So that actually brings me to the end of this section of the topic. And when I come back, we're going to finish up talking about how the urine is actually concentrated and that hormonal regulation of the nephron in terms of water conservation.